After an anomaly in an aerospace fly-by-wire control system, engineers begin a post-flight analysis to decode what happened in the cockpit. The primary objective is to extract flight telemetry and reconstruct the pilot's exact physical inputs at the moment of the failure. In this scenario, the black box records a final aerodynamic elevator deflection of exactly 10 degrees. To recover the initial state, engineers apply the system's inverse function, calculating backward from the physical output to find the original mechanical input. But here, the protocol hits a mathematical paradox. The reverse calculation fails to provide a single answer. Instead of one stick angle, the math produces an infinite set of possibilities: 6 degrees, 7 degrees, 8 degrees, and beyond. The aircraft's true physical state history has become unrecoverable. The mechanical architecture of the linkage has effectively erased the pilot's intent. This is a breakdown in structural invertibility, the governing property that dictates whether a system's history can ever be known. Complex engineering systems are built on sequential processing, where the output of one subsystem serves as the direct input for the next. Mathematically, this is known as function composition, a chain of mappings that connects the pilot to the aircraft's control surfaces. The inner mapping, function F, defines how the mechanical linkage translates the stick angle into hydraulic spool displacement. The outer mapping, function G, defines how the hydraulic ram translates that displacement into the final elevator deflection. By combining them, we get a composite equation that governs the entire end-to-end response of the flight control system. To reverse this process and perform a post-flight analysis, the system must possess structural invertibility. This requires the system to maintain a specific two-way relationship called a bijection. For a mapping to be a bijection, it must first be injective, meaning it is perfectly one-to-one, with every unique input leading to a unique output. It must also be surjective, covering the entire range of possible outputs without leaving any states undefined. When both conditions are met, every output has one and only one unique input, making the backward trace mathematically certain. In our aerospace linkage, the inner mapping doubles the input angle. However, the system is physically finite. The outer mapping is constrained by the hydraulic ram, which features hard mechanical limiters at 10 millimeters. If the pilot deflects the control stick past 5 degrees, the system reaches its breaking point. The linkage attempts to force the spool displacement beyond that 10 millimeter threshold, but the ram hits its mechanical stop, capping the elevator deflection at 10 degrees. We can see the breakdown on the graph. Distinct inputs, 6 and 7 degrees, climb the axis only to collapse onto the exact same 10-degree output. This flat line represents the destruction of injectivity. The system has entered an ambiguous one-to-many configuration. Because physical stops force unique inputs to become indistinguishable outputs, the mechanical dead zone permanently erases the history of the flight. This mathematical collapse applies to every engineering discipline, including avionics and environmental sensors. These sensors use signal conditioning trains to translate raw physical pressure into analog voltage and finally into digital telemetry. Here, the inner mapping is a transducer, and the outer mapping is the 12-bit analog-to-digital converter that quantizes the signal into digital counts. A failure occurs if an analog amplifier rails out, reaching its maximum supply voltage. It can also happen when the ADC hits its quantization ceiling of 4095 counts. At this envelope boundary, surjectivity and injectivity fail simultaneously. To prevent this, engineers must actively constrain the composite transfer function to its linear range. Maintaining data integrity requires forcing the system to operate strictly monotonically, staying well away from the physical extremes where invertibility dies. Software and cloud architectures offer a reprieve from these physical boundaries. Cloud pipelines process data through algorithmic sequences rather than mechanical linkages or voltage-limited amplifiers. The inner mapping serializes raw JSON transaction strings into binary byte arrays. The outer mapping uses cryptographic ciphers to convert those arrays into secure network packets. This sequence forms the composite mapping for end-to-end data transmission. This digital architecture is designed for perfect inversion. Because there are no physical stops, every distinct input maps to a unique output. Without voltage rails or mechanical limits, the mapping remains injective across its entire range. This structural preservation ensures the original data is completely recoverable, allowing for perfect deserialization at the receiver with zero information loss. The difference between these systems illustrates the fundamental challenge of engineering across different mediums. Software architectures are engineered to satisfy the bijective requirement throughout their execution range. In the physical world, mechanical stops and voltage ceilings naturally destroy injectivity, creating unresolvable ambiguity. Robust system design requires more than just ensuring a functional forward path. It requires active structural preservation to ensure the reverse mapping remains analytically defined. Whether designing hydraulic linkages, calibrating sensors, or writing code, the underlying mathematical laws remain identical. When engineers ignore these boundaries, they transform clear telemetry into unreadable black boxes. Mastery of the machine requires recognizing that bijections are the only thing standing between a functioning system and a complete loss of history.